What if I told you that more than 5 million engines from GM, Toyota, Honda, and Hyundai are failing right now? Some are even catching fire with families inside. $70,000 trucks are dying at just 30,000 miles. There have been 42 fires, 12 injuries, and manufacturers are allegedly keeping the full truth quiet. Your engine could be next. Here's what they don't want you to know. The disaster by the numbers. Let's start with figures that should concern every car owner watching this because your vehicle could be included. General Motors has recalled 720,000 vehicles equipped with the 6.2-liter V8, and that's only part of the story. Another 280,000 are under federal investigation. GM has received more than 28,000 complaints, with over 14,000 resulting in complete engine failure and total power loss. There have been 12 reported injuries and 42 engine fires, not minor overheating or smoke, but actual flames under the hood while people were driving Silverados, Tahoes, Yukons, and Escalades, family vehicles rendered useless. Toyota, long known for durability, recalled 102,000 twin-turbo V6 engines in 2024 and later added another 127,000 in 2025. This affects brand-new Tundras, high-end Lexus LX 600 models, Sequoias, and even hybrids still being investigated. Honda recalled 250,000 of its well-known 3.5-liter V6 engines due to rod-bearing failures. When those bearings fail, internal components can destroy the engine at high RPM. On top of that, NHTSA has launched a probe into 1.4 million Hondas dating back to 2016. Hyundai and Kia have recalled 1.5 million engines since 2017, and in some cases, replacement engines have failed in the same manner. Altogether, this totals more than 5 million engines and nearly $8 billion in damages. This goes beyond a routine recall. It really resembles a widespread engine failure crisis, and it's becoming personal for many owners. The power density and ultra-thin oil issue. So, what's driving this nationwide engine problem? An investigation by Automotive News in December 2025 examined the issue by consulting university researchers, independent mechanics who've disassembled hundreds of failed engines, and industry insiders. Their findings were, honestly, pretty troubling. Modern engines are being pushed to unprecedented limits. Automakers are striving for record horsepower per liter, performance levels that were once limited to race cars. Today's engines operate at higher temperatures and cylinder pressures than older designs ever faced, all while being significantly smaller. For comparison, a 6-liter V8 from the 1990s produced around 360 horsepower, which is about 60 horsepower per liter. Today, Ford's 2.7-liter EcoBoost generates 325 horsepower. That's roughly 120 horsepower per liter. The 3.5-liter EcoBoost Raptor actually reaches 128 horsepower per liter, so that's roughly double the power density, with less material to manage all that stress. At the same time, to meet EPA and CAFE fuel economy targets, manufacturers moved to much thinner oils. Traditional 5W30 and 10W40 oils gave way to 0W20, 0W16, and even 0W8, fluids that are, honestly, extremely thin. While these oils may slightly improve fuel economy, they require extremely tight tolerances and, near-perfect machining and cleanliness. Even minor imperfections can lead to serious damage. The role of contamination is another big factor being discussed. There's this thing called microscopic metal debris left behind during manufacturing, known as swarf. During machining and honing processes, fine metallic particles can actually remain inside the engine. If they're not completely removed, these particles can circulate with the oil and cause wear. Engine builders explain that even a tiny fragment trapped between a bearing and crankshaft can act like abrasive material, gradually scoring surfaces and, accelerating failure. Thorough cleaning is possible, but at mass production levels, with factories producing thousands of engines daily, achieving hand-built precision is extremely challenging. With thinner oils, tighter tolerances, and harder bearing materials, engines have less margin for error. There's just less ability to absorb contaminants, meaning small issues can escalate pretty quickly. The perfect storm of modern technology isn't just about a single flaw, it's really about several modern technologies interacting all at once. Start-stop systems, for example, shut engines off and restart them over and over, and each time oil pressure drops briefly. Then you've got variable oil pumps, which depend on electronic controls. That adds complexity and, honestly, more chances for something to go wrong. Turbocharging is another factor. It pushes cylinder pressures way up and really depends on having clean, properly flowing oil. Direct injection, meanwhile, increases combustion pressures and temperatures, and it can also lead to carbon buildup. When you put all these things together, it's no wonder people talk about a perfect storm. On top of all that, engines built during the 2020 to 2022 period had to deal with supply chain disruptions, staffing shortages, and quality control issues. Some manufacturers even reported contamination or components that didn't meet spec during that time. There's also cylinder deactivation systems which shut down half the cylinders when the engine is under light load. But when those cylinders reactivate, it creates uneven temperatures and added mechanical stress. Now, each of these technologies can boost efficiency on its own, but when you combine them, engines end up running under higher stress, with less room for error. There's this ongoing debate, design versus debris. Some independent engine builders argue that certain failures might actually point to design limitations, not just contamination. For instance, in at least one teardown of a failed twin-turbo V6, the main bearings were really badly damaged, even though the rod bearings, supplied by the same oil system, looked fine. Stuff like this sparks debate about whether oil passages are sized right, if bearing clearances are correct, or if the load capacity is high enough. In other cases, manufacturers have changed oil viscosity recommendations during recalls, like switching from 0W20 to 0W40 in some engines. Critics say that using a thicker oil might help protect engines under high stress, and it makes you wonder if those ultra-thin oils are really up to the task for long-term durability, especially in high-output engines. Manufacturers usually blame failures on contamination or isolated defects, but independent analysts sometimes think there are bigger design trade-offs at play. Honestly, figuring out the real cause often takes a detailed engineering review. Another big factor is regulatory pressure. Fuel economy rules, like the corporate average fuel economy or CAFE standards, require automakers to hit higher and higher fleet-wide efficiency targets. To get there, companies have turned to smaller, turbocharged engines and ultra-thin oils to squeeze out better fuel economy numbers. Trying to reach high miles per gallon averages with traditional big displacement engines just isn't practical anymore, and that's pushed the shift towards smaller, more stressed powertrains. Whether the main problem is contamination, design compromises, regulatory pressure, or, honestly, a mix of all three, one thing is clear. Modern engines are running closer to their limits than ever before, and when engineering margins get tight,